And let's we'll get started and we'll actually learn some real calculus today, okay? So, section 2.1 starts our study of calculus, and the section is entitled Tangent and Velocity Problems. Tangent and velocity problems. They're two things that are really related, and I'm hoping by the time we get done you understand why they're related. And we're going to start off, like I mentioned before, I like a starter question. By the way, what was the starter questions on last week's notes? What do people struggle with when they take calculus? And it's the pre-calculus stuff. It's the stuff that we talked about last week. We're now going to talk about some actual calculus ideas. So this says, what would be the end result, or we're going to use the word limit, if you continued each of the following patterns. So let's take a look at this one right here. 1, 1/2, 1/3, 1/4, 1/5. I mean, we can spot the pattern pretty easily. The next one in line would be 1/6, then 1/7, and so forth. So what would be the end result of that? If I just continued that forever, okay, the end result would be, okay, very good. Okay, it would be a good word there. It would be approaching zero. It would never actually equal zero, but we'd get closer and closer and closer and closer to zero, okay? If I stood 4 feet from the wall, and then I walked halfway to the wall every second. So I'm 4 feet away from the wall, second goes by, then I'm 2 feet. Then I'm 1 foot, then I'm half a foot, then I'm 1/4 of a foot, and so forth. What would be the end result of that process? Where would I end up? Well, if this is the wall right here, and I go halfway, and halfway, and halfway, and halfway, and halfway, and halfway, and halfway, where do I end up? The wall. I end up at the wall, okay? So the limit would be the wall. Now, just like in this case, I would never actually reach the wall, okay?
But the wall would be 1 whole unit away.
Yeah. Well, that's. Okay. Could I go past the wall? Let's put it that way.
No.
I couldn't go past the wall. That would be my limit. Okay. Would be reaching the wall. Okay. And then let's take a look at this one right here. This hopefully looks a little bit familiar. If I take 1/2 plus 1/4 plus 1/8 plus 1/16 and so forth, what do I end up with? Okay. You're approaching 1. And you've probably all seen this example.
I was mixing B and C.
That's okay. So you've probably all seen this example. This is a geometric series. You probably saw this in 1050 where you take a piece of paper, tear it in half, and then you just keep tearing it in half and half and half and half. And what ends up is all the paper that you had in your hand to begin with ends up in this stack. You can just get to the point where you're splitting atoms and putting them over here. The point is you're never going to get all of the paper from your hand into the stack of paper over here, but is this stack of paper ever going to be more than 1? It's not going to be more than 1, and it's going to get closer and closer and closer and closer to 1 the further you go, okay? So for all intents and purposes, that's what it would reach, or that would be the limit, okay? So this is the idea that makes calculus possible.
So
yeah.
is the difference between A and C just because there's plus signs in it? Because they're adding 1/2 plus 1/4?
Right. Here we were talking about just looking at the terms, okay? What happens if we extended this out? They get smaller and smaller and smaller. And what's the smallest number you can have? 0. Okay. Here we're taking these and we're adding these together. Okay. So if we add these together, we get 3/4. If I add that one, I get 7/8. Then I get 15/16. Okay. Does that ring a bell? Mm-hmm. Have you seen that before? Okay. All right. So let's talk about what calculus is. And I like to start off this way because we're actually going to end the course when we study chapter 5 and 6. We're going to kind of wrap this all together. Okay. And one of the questions on the last exam that I give is, what is calculus? It's not a calculus problem, it's just a verbal description of what calculus is. So we're going to kind of start off with this. Here's what calculus is. It's about 2 main branches, 2 main topics, okay? One is about rates of change. We talk about rates of change for the most part in this class, and that's something called differential calculus, okay? Deals with derivatives, which we'll do a ton of in chapter 3. Okay? And then the second part of calculus is about how rates accumulate, and this is called integral calculus. Okay? So there are 2 branches of calculus. We're going to study differential calculus for the most part this semester, and then toward the end we'll get into some integral calculus, and if you take Calc 2, that's a lot of integral calculus in that course. Okay? So these 2 branches of calculus are both based on the same idea. It's the idea of a limit. And in chapter 2, what we're going to do for the most part is just introduce a lot of the concepts and techniques behind finding limits. Now, we had some examples up above that were slightly mathematical. We're going to do things that are very, very mathematical, okay? We're going to be dealing with limits of functions and different things like that, not necessarily verbal descriptions like we've got here, okay? So they were pretty informal, but the idea is this. The limit is the end result that is approached by a process or a pattern. So the limit is the end result that is approached, and Ben used that word when he was talking about this. It's the end result that is approached by a process or pattern. Okay? The limit does not necessarily have to be reached in order to be the limit. So we didn't actually reach 0 in part A. We didn't actually reach the wall in part B. Okay? And we didn't actually get a whole stack of paper here that was equal to one whole piece of paper there in that example. So it just has to be approached, all right? Just has to be approached, okay? And the idea that we can figure out what quantity is approached by a particular process is the foundation of calculus. So in other words, if we said this really succinctly, you really need to know what limits are and how to find it, because limits make calculus possible. Okay, if we weren't able to calculate limits or compute limits, we wouldn't be able to do calculus. Okay, so they're really important. And we're going to start our study of calculus by looking at a couple cases where we can involve limits or involve extending a process kind of out forever and just kind of get some numeric feel of what we're talking about. And these are classic calculus problems. This is what people were wondering hundreds of years ago when they said, well, there's got to be an end result of this. How could we make this work out? These are the ideas that they were struggling with. We've kind of contrived these a little bit to make them a little bit easier to work with. But here's the deal. It says, find an equation of the tangent line to the parabola y equals x squared plus 2 at this point right here at 1, 3. So P1, 3 just means the point at 1, 3. Okay? Now, I do want to point this out. Most of you just got out of trig and you used the word tangent in the trig setting. We're talking about tangent in the geometry setting as far as circles go and that sort of thing. Okay, so tangent in this case means a tangent to a circle just barely touches it in one point. That's what we're talking about here. Okay, the tangent line just touches it right there. That's the only place that it's touching. Okay, and what we're after is we want the equation of this line right here. So we want y equals mx plus b, the slope-intercept form of that line right there. Okay, that's what we're after. Everybody understand? Equation of the tangent line. Okay, so like we talked about last week, what two things do you need to write the equation of a line? Okay, you need a point and you need a slope. Now, do we have a point? Yes, we do. We've got a point. Got that part taken care of. Now, when we mentioned this last week, I think we said you've either got to have a point and a slope or enough information that you can figure out the slope. Okay, and here's where it gets a little bit sticky. Here's where the limits and the calculus comes in. Okay, I could take a guess at what the slope of this line is. I mean, I drew that actually. This is pretty darn good. I did a really good job of drawing that. Okay, in fact, I would dare say that is nearly perfect, and I don't do that very often. I could take a guess at what the slope is. Okay, but I want to know exactly what the slope is. Okay. So here's how some mathematicians, some curious people who were pretty good thinkers a couple hundred years ago, here's how they approach this. Okay, so we're going to introduce some notation. Okay, we're going to use the slope of the secant. So we're going to change from, and this is what mathematicians often do, we're going to change from a problem that we're like, I'm not quite sure how to do that, to something that we do know how to do. Okay, now I can find the slope of a secant between 2 points all day. You give me 2 points, I know what the formula is for the slope between 2 points. So we only have 1 point here. We're going to take this and we're going to make it so we've got 2 points. So we're going to find the slope of the secant between 2 points P and Q. And we're going to use a table to represent and keep everything straight here. So I'm going to use the point P. I'm going to call this the point of interest. This is where we want to find the slope at. And Q is going to be point X and Y, where X is the value given to us in the table, and Y would be what I get when I plug into this right here. okay? So this table is not an XY table. These are X's, and these right here are slopes. So we've got to do some calculations right here. So the point is 1, 3, and the other point is, what am I plugging in for X? 0. And what do I get when I plug a 0 in here? I get a 2. Let's represent this geometrically. Let's go over here to the graph. 0, 2 is right here. So can I find the slope of that secant right there? Yes, I can. Pretty easy to do, right? I can look at it graphically and I can figure it out. And I can also figure it out using the slope formula. So the slope formula, so the slope between P and Q is going to be, now I'm going to do it this way just for sake of this. I'm going to switch the order of these because we normally go from left to right. So that this is going to be my x2 and my y2, and this is going to be my x1 and my y1. So this is going to be, well, let's see. Do I want to do that? No, we'll just leave it that way. Yeah, we'll just do it this way. We'll do x2, y2. This will work fine. And x1, y1. Okay? So I'm going to have 2 minus 3, right? And 0 minus 1. So that's going to give me -1 and -1, so my slope is 1. Okay, now to kind of keep things straight, this is the work that I had to do in order to find the answer that goes right here. Because if I'm finding the slope between 1, 3 and xy, there's that xy that we found over here, this slope is 1. So if I find the slope between 0 and 1, I get 1. Slope there's 1. Okay, now, is this line a decent estimate for that line? Is the slope of that blue line a decent estimate for the slope of the red line? It's not very good, right? So here's what we're going to do. Okay, and again, bear with me. I know this seems a little bit tedious. What we're going to do is we're going to take this point. Instead of doing from 0 to 1, we're going to go from 0.5 to 1. So this is going to be 0.5 over to here. So this is what it's going to look like geometrically. We're finding the slope of the secant between those 2 points. So we're going between 1, 3, and the other point is 0.5, and you're going to need a calculator for this probably. It'll come in handy in the long run, even if you can do this in your head. Okay? What do I get when I plug in 0.5? I get 2.25, right? Okay, I get 9/4, so 2.25. So if I find the slope between P and Q, this is what I end up with. I'm going to do 2.25 minus 3, and I'm going to do 0.5 minus 1. So this is going to give me, correct me if I'm wrong, 0.75, and then this is 0.5, right? So what do I get? I get 1.5, right? 1.5. Correct me if I'm wrong. Okay? So I get, I'm going to write it as a fraction. I'm going to write it as 3/2. Okay, now, should have done that in blue. Okay, is the slope of this line a good approximation for the slope of the tangent line that we're actually after? It's better, right? Okay, and the fact that it's getting better leads us to think, well, wait a minute. If all I have to do is just do some brute force numeric math here, I mean some simple calculations like this, well, let's do this. Let's go between 1, 3, and what's the next point? 0.9, comma, and what do I get in if I plug in a 0.9? I get 2.81, which means I've got 2.81 minus 3, and I've got 0.9 minus 1. So this is going to be negative 0.19, right? Divided by 0.1, or negative 0.1, and I get 1.9, right? Move the decimals over, I get 1.9. Now, again, geometrically, this is what it would look like. 0.9 is about right here. So let me draw in a green line. Now, it's really tough to do this. Okay, can you see the green line there? It's better, isn't it? Okay. Well, if what we've been doing looks pretty good, let's just continue this. Let's get really, really close together. Now, think about what we did to begin with. We wanted to find the slope of a line that touched this curve in just one point. Okay? You can't find the slope if you just have one point. You need 2 points. So what we did is we said, well, let's find this slope, then let's find this slope, and let's move these 2 points closer and closer together. So let's get them really, really close. Let's get them within 100th of each other. So we're finding the slope between 1 and 3, 1 comma 3, and the other point is 0.99 comma, help me out here, can't do that one in my head. What is it? 2.98? Is that right? Good there? Okay, so I've got 2.98 minus 3, and I've got 0.99 minus 1. This gives me, correct me if I'm wrong, negative 0.01 on the bottom, and this is going to give me, is that right? Do we have enough decimals there?
It's 2.9801.
Okay, 2.9801, okay? And that's the whole decimal, right?
Yeah, that's it.
Sounds a little better. Okay, this is going to be negative 0.0091 or 19?
0199.
Okay, 0199. There we go. And if you go ahead and do the division, of course the negatives cancel and we end up with 1.99. Okay, we'll look at the slopes here. Started off with a slope of 1, 1.5, 1.99, or 1.9 and 1.99. What do you think would happen if we did this?
1.999.
Yeah, it's probably going to be several nines in a row or something like that. Okay, so if we started off with this slope and moved the points closer together and moved the points closer and closer together, what would your guess be for the slope of the tangent line, given the fact that we got 1, 1.5, 1.9, 1.99, and that we guessed the next ones? Yeah, we're going to guess that it's going to approach 2. Okay, now, any questions there? It's a pretty simple idea, isn't it?
Yeah.
Okay. Do any hard math so far? Keeping this table straight is a little bit weird, but no difficult math so far. Okay, well, what we did is we always used points on the left side of the point of interest. We were always using 0 and 0.5 and 0.9 and 0.99 and so forth. And we got something that was approaching 2, but maybe we ought to check on the other side. There's nothing special about checking the slopes on this side. So let's do this. Let's do this one over here. Let's check between 1 and 2. So let's do this point right here. In other words, we're going to use this secant line to approximate that one, to take a guess. So we're going to do the same thing again. So we're going to do between 1 comma 3 and 2 comma, what happens if I plug a 2 into this? I get a 6. So we'd have 6 minus 3 over 2 minus 1, so I end up with 3. Does that look like it's steeper? Does that look like a slope of positive 3? It does, but then we're going to do the same idea. Okay, and to just make this a little bit less tedious, let's do this. Would you 4 over here, would you compute the one for 1.5? Would you guys right here in the middle, would you compute the one for 1.1? And would you guys over there, would you guys compute the one for 1.01? And let's see what they are. You guys are doing 1.5, 1.1 in the middle, and 1.01 over here. Okay, you got the 1.5 figured out? What's the slope? What'd you get? Yeah, that sounds a little bit better. Okay, so that's going to be a slope of 2.5. And again, here's what we're doing graphically speaking. What I'm doing is I'm saying, look, if I go between 1 and 1.5, I'm finding the slope between these 2 points right here. Okay, it's even hard to see because they're so close together. Okay, and then with 1.1, what did you guys get with 1.1?
2.1.
So you got 2.1. Okay, move them even closer together. And then with 1.01, you guys confirmed, didn't you get 2.01? Sound right? 2.01. What's that? Oh, you're right, it is. Oh, did I? Let me see, did I write something? Yeah, here we go. This should be a 0, 1. That should be a 0, 1, which makes this 2.01. Okay? Catch the mistake there? Okay, everybody good? Okay, let's come back up to the picture here and let's take a look. Okay, so here's what we did. We wanted to find out what the slope of this line was right here. Okay? And what we did is on either side, we said, well, let's find the slope of the secant line. So we did between these 2 points. Said, that's not very good. So we said, let's take another guess. Let's do these 2 points. And that's a little closer. And we said, well, let's do these 2 points. And that's a little closer. Okay? And continued doing that from the right side and guessed that the slope was going to be approaching 2. And then we did the same thing over here. We said, well, look, let's use this point over here and let's find the slope of that one. And then let's do it for a point that's closer. In other words, take the 2 points that you're using to find the secant line and let's move them closer and closer and closer together and see what would happen effectively if we could put those points right on top of each other. Does that make sense? And so what is our guess as to the slope of that line? I mean, do we have pretty darn good confirmation that coming from the left side as we approach 1, the slopes would get closer and closer to 2, and coming from the right side, coming from over here, the slopes get closer and closer to 2. So they start smaller than 1 and get close to 2, and start bigger than 2 and get closer to 2. Does that make sense? Okay, so what can we conclude about the slope on that curve right at that particular point? What would we say the slope is?
2.
Okay, so we're going to say that the slope is 2. And then it says, what's the equation? So in order to find the equation, I'm going to plug this into point slope form. It's going to be y minus 3 equals, the slope is 2, and x minus 1, and then we'll just move that around, put it in slope intercept form. So this is going to be y minus 3 equals 2x minus 2. So this is y equals 2x plus 1. Y equals 2x plus 1. Everybody good with that?
Yep.
Okay, now, what I want you to do is take a look at that original one. Remember I said I did too good a job drawing that? Y equals 2x plus 1. Does that look like it has a slope of 2? Does it look like it crosses the y-axis at 1? Yeah, so there's the equation for the tangent line. Okay, any questions?
So
Yeah.
tangent line is it barely touches it, but at that one point. But what if you could go like this way down and go through it?
You mean like that?
No,
Or
like
what?
go through 0.13 or 0.14 or
Oh, I see.
yeah, like that. But then it cross the other side. of the
It
ground.
does touch it. So what if we had a curve that did something like this? Came down and then went like that? Is that what you're talking about?
No, like
He's
perpendicular.
saying just goes through the point. Just
Oh, you mean like
Yeah.
did something like this?
Yeah.
it would
Wouldn't be a tangent
Wouldn't
line.
be a
The
tangent
way tangent lines are defined.
Okay.
Okay. And so think about what a tangent is on a circle.
Mhm.
If we have a circle, a tangent would be right here. It's not this one right here. That has another name. Okay, that's called a radius, and this meets at a right angle. The interesting part is true here also. So if I draw this line that you were talking about right here, it would actually be perpendicular to the tangent. We call it a normal line.
Mhm.
Okay. Good question though. Okay. So another way to think about what a tangent is, and this applies to a circle and this right here, a tangent line would be if you had so say we had a yo-yo and we were swinging it around like this. If you let it go right there, the tangent would be the path that it would travel on. It's the direction of its travel. So if we had, say, an object in orbit or something like that that was following this path, if it was suddenly let go from a gravitational pull, it would follow along this line right here. If we found the tangent right here, it would head off in that direction. Stuff like that, okay? We're getting a little too deep for how far we're in the course right now, but good questions. Anything else? Okay, yeah.
So when it crosses 2 points, that's the secant line, right?
Yeah, other than that other curve that I drew that kind of curved over here, I mean, we kind of talked about tangents in neighborhoods. We don't really care if it intersects it somewhere else. Okay? If you want more detailed information and have what-if questions, come see me afterward. Okay? All right. So let's take a look at where that type of problem actually came from. People were curious about this type of thing. So a rock is launched vertically upwards. So they throw it straight up in the air, okay, and then it comes down. It's got an initial speed of 96 feet per second, and we're going to neglect air resistance because that's what good mathematicians always do. Okay, and we're going to keep track of the position. And again, we'll use the type of notation all the time. You're probably familiar with this all the time, but we generally use S to represent position. Okay, we could maybe argue about why. Okay, and we're going to talk about this in terms of feet. So we've got this position function that represents the height of the rock above the ground after t seconds. So we've just got this equation that will tell you how high the rock is. So if you put in a 0, where is the rock? It's on the ground. Its position is 0. Okay. If you put in a 1, that would represent the height of the rock after 1 second. Okay. So here's what we've got. Find the average velocity between each pair of times. Average velocity. Okay, average velocity. That's going to be in feet per second. How fast is it traveling on average? So here's what we're going to do. Let's see. If we plug in a 1, so let's go ahead and do that. If I plug in a 1, I end up with, that's a minus 16 plus 96. So at 1 second, it's 80 feet off the ground. And at 3 seconds, how high is it off the ground? Say 144. 144. I'm just kidding. I don't know what it is. I think it's 144 though.
You're right, it's 144.
Yeah. And this, I mean, see how nice this is that the diagrams are already set up for you? Okay, 144 feet. Okay, well, the easy way to do this is say, look, it took me 2 seconds to go from 80 feet to 144 feet. So if I was at 80 feet to begin with and I got to 144 feet, how many feet did I go?
Wait, it's not, how is it 144 feet? Because you put the 3
Okay.
in the
Yeah,
2,
plug it in. That's going to be 9 times 16.
which is negative 144.
Right. And then what's 3 times 96?
Oh,
Okay, don't forget that part. We good? Okay, how many feet, Sheila?
64.
64 feet, okay, in 2 seconds, right? Well, the most straightforward way to do this problem is to just use that formula that says distance equals rate times time. If we want to know how fast we were going, we traveled 64 feet. Don't know what the rate is, but we did that in 2 seconds. So the rate would be 64 feet divided by 2 seconds. And what do we end up with? 32 feet per second. Okay? Okay, but that's the average velocity. And we did this using a formula that we're all familiar with. Okay, but in the long run isn't quite as good. Okay, so we're going to do this in a little bit more sophisticated fashion. So here's what we're going to do. We're going to use this notation. We're going to call this V average for the average velocity, okay? And we're going to do this. We're going to do S of T1 minus S of T naught. Hopefully you're familiar with that type of terminology. And then T1 minus T naught. So if we were to say this in words, and I like coming up with phrases to help you remember what we're looking for, this is the position at time 1, and this is the position at time 0. Okay, so this is the initial position, and this is the end position. So this is end position minus whatever the starting position was. And T1 is the end time, and T0 is the beginning time. So this is going to be end time minus start time. And the reason we're going to do it this way will be pretty clear in just a second. You're going to see some things that should look pretty analogous. So if I want to know what the average velocity is between 1 second and 2 seconds, I'm going to find what s of 2 is and subtract s of 1 and put it over 2 minus 1. Now remember, this is position in feet, and these are times down here, so these are in seconds. So although this looks like kind of a weird way to do it, isn't this quantity going to give me a velocity? If I've got feet on top and seconds on the bottom, isn't that a velocity? It is. Okay, so let's figure out what this is. Now the cool part about this is, look at the denominator. It's 2 minus 1. 1 second. I only let 1 second elapse from second 1 to second 2. And this is s of 1, the position at 1 second. Didn't we already compute that? Wasn't that 80? So this is going to be minus 80. And if you plug in a 2, you get 128. Okay? This is going to be 4 times negative 16. So that's going to be negative 64. We're going to plug in a 2. That's going to be 192. Subtract the 60. You get 128, right? So you get 128. Notice that it happens to be the numbers that I've got right here. Okay? Very nice. So let's see, if I subtract there, that's going to be 48 on top. So this is going to be 48 feet per second. Okay, now, if we look at these two problems that we just did, these two average velocities that we just figured out, between 1 second and 3 seconds, we covered 2 seconds, and we covered 64 feet, right? And we did 64 over 2 seconds. That's what produced our answer of 32 feet per second, right? What I did right here is I said, let's just go from 1 to 2. So let's go from here to here. This was 1 second, and this was 48 feet, right? 48 feet over 1 second, that produced my 48 feet per second. Well, what are we doing here? Does this look familiar? Aren't we just computing a slope? Yeah, we are. Okay, so that average velocity formula is like having y2 minus y1 over x2 minus x1. That's what it's like. So let's do one more. And notice what we're doing here. Instead of between second 1 and second 3, or second 1 and second 2, here's what we're going to do. We're going to do between 1 and 1.5 seconds. So we're going to do this right here. We're going to find the slope of that secant, or in other words, the average velocity between 1 and 1.5. So that's going to be s of 1.5, and grab a calculator if you would. But the only part that you need from this is just the s of 1. That's all you're going to need a calculator for. Because we already figured out, hey, our starting point was 80. Our starting position was 80. Our end time minus our start time is going to be 0.5. And remember, that's going to be seconds here and feet on the top. And somebody help me out here. What is s of 1.5? How many feet off the ground is it 1.5 seconds after we launch this rock?
180.
108. Okay, so this is 108. That's going to be 28 divided by 0.5. That's going to make it bigger than 28 because we're dividing by a decimal here, number between 0 and 1, and that's going to make it 56. 56 what? Feet per second.
How'd you get the 108?
Plugged in 1.5 into
there.
this. Any questions? Yeah.
So I know it's used very interchangeably, but relation. Velocity is a vector quantity, so you have to have a direction with it. So really, you should say
Speed.
56 feet per second upward or 56
You are correct. So Juan is a physicist. He's very technical about this, and we do ignore that for the time being. We'll get to that a little bit later. But technically, you're right. Yeah, we should say upward or downward. What we've done here is we've indicated that upward is the positive direction, down would be the negative direction, which we'd get if we found how fast it was going downward. Okay? All right. So let's take a look at this. Again, this average velocity formula is just like finding the slope. In fact, we can draw a picture of what it looks like and how we'd find slopes on this position curve. Okay? So finding the average velocity is a lot like finding the slope of the secant. Between 2 points on, okay, now this is I do make a big deal about this. This is a position curve. So again, just to restate, average velocity is going to be s of t1 minus s of t0, where it was to end with minus where it was to start with, and then t1 minus t0, okay, just to emphasize. So if you think about what's going on here, and we've kind of approached this problem backwards from what they did historically, if we move these 2 points closer and closer and closer together, aren't we going to get really close to how fast the rock was going right at 1 second? If we slide these 2 points closer and closer together, if we reduce our time increment going from 1 to 2, 1 to 1.5, 1 to 1.1, and stuff like that, we're going to get really close to how fast it was going right at 1 second. Okay? So it wouldn't be the average velocity anymore. It would be something that we call the instantaneous velocity. Okay? Now, this can get a little bit tedious because every time you compute one of these, this is what you've got to do. You've got to do an s of 1.5 minus s of 1 over 1.5 minus 1. And here's how we're going to make this a little bit easier. This is going to be 0.5. It's just the difference between the two of these. It's just the difference between 1 second and 1.5 seconds. This is always going to be minus 80. And all I need to do is figure out what s of 1.5 is, which we did a second ago. We ended up with 56 feet per second. Okay, now we're going to break the class in half. Would you guys do the one for 1.25? And would you guys do the one for 1.1? So what we're doing is we're decreasing this time interval. So this is going to be 1.25 minus 1, s of 1.25 minus 80. And they're going to figure that one out. And over here, you guys are going to figure out s of 1.1 minus s of 0, or s of 1, which would be 80. And this is going to be 1.1 minus 1. So when you get it, confirm with somebody around you, see if you did all the math right.
I got 60. 60.
That's 15. Yeah, 15 times 4 is 60.
Okay, s of 1.25 is, isn't it 95 or something?
Yeah.
95. So this is going to be 15, so that's going to make this 30, right? Oh, sorry, yep. Yeah, sorry, divided by a quarter is going to make that 60. So that's 60 feet per second. Okay, and for you guys over here, s of 1.1, isn't that like, let's see, 86.24? Is that what it is? So 86.24 minus 80, so this is going to be 6.24 divided by 0.1. So that's going to make this answer 62.4 feet per second. You with me? Any questions? Okay, so here's what somebody was wondering in order to come up with a problem like this. Again, we've approached this a little bit backwards. They were saying, what happens if I throw a rock straight up in the air with all of these conditions? How fast is it going exactly 1 second after I throw it in the air? In other words, what is the instantaneous velocity? Okay? It's going up, but how fast is it going up? Okay, well, we've used different time points and basically the distance rate time formula to figure that out. Changed it into a geometric formula where we were figuring out, well, what's the slope between these two? Because that'll be the same as the average velocity. What's the slope between these two and these two and these two? See how this is a limiting process? We want to get these two time points closer and closer together. Well, how close did we get them? How far apart are those? 0.1 or a tenth of a second. Okay? Well, if you've got a graphing calculator, if I have time, I'll come back and do this in just a second, and I'll show you how you can kind of program your calculator to do this, at least on the home screen. Let's do this. You know, if I had 56, or we had 32, then 56, then 60, then 62.4, it's clearly getting bigger, right? But let's shrink this time interval. Let's do this. Let's do between 1 and 1.0001. Let's do that. So throw that in your calculator. What goes in the denominator? 0.001, 3 zeros and a 1. At 1, it was at 80. And all I need to do is figure out what is S of 1.001. So I'm giving a 10,000th of a second. A 10,000th of a second difference. It could hardly move in 10,000ths of a second. Okay, can somebody tell me what S of 1.0001 is and double check with your neighbor, make sure you got it right before you tell me? Juan, what have you got?
I got 80.0063998.
Okay, so if I do the subtraction there, I get this. I get 0.00639984, and I'm dividing that by 0.0001. How many places do I move the decimal? Say 4. You'd move it 4 places on the bottom and 4 places on the top. That would put a 1 on the bottom, and that would put a 63.9984. Whoops. And that is in feet per second. So if you had to take a guess at how fast it was going exactly 1 second after we threw this rock in the air, how fast would you say?
64.
You'd say about 64. Now, how could we confirm that?
Go the other way.
You could come from the other side, okay, and it would probably be getting closer and closer to 64 from the other direction. These are smaller and getting bigger. They'd be bigger and getting smaller, okay? Right now, we can't confirm that for sure. We can just take good guesses. We can make conjectures, okay? But could I shrink that time interval? Could I give it a millionth of a second, and could you take those nice little calculators and compute what the average velocity would be on a millionth of a time second interval?
Yeah.
You could. And guess what? It's going to be really, really close. We're going to have a bunch of 9s. Okay? So it's getting really, really close to 64. So that would be our guess. Okay? So in the couple of minutes that we've got left, and that'll be good. There's a challenge problem at the end. If you can get to that, that would be great. Okay? Here's what we want to do. We want to sum up and we want to look at how to apply this to a different setting. On a position function, average velocities are the same as the slope of the secant lines for any two given points. So if you want the average velocity, all you're doing is finding the slope of the secant line. If we move those 2 points closer and closer together, so this idea that we were talking about at the beginning of class, of kind of the end result of a limiting process, okay? If we move those points closer and closer together, the slope of the secant line approaches the slope of the tangent line. So that means the average velocity would get closer and closer to the, we called it the instantaneous velocity. So this is problem number 2. It's out of your book. It says a cardiac monitor is used to measure the heart rate of a patient after surgery. It compiles a number of heartbeats after T minutes. Now, they make up problems in textbooks. They usually have some basis in truth, but we just, put a stethoscope on him and count, right, to figure out what his heart rate was. Okay. When the data in the table are graphed, the slope of the tangent line represents the heart rate in beats per minute. Might be useful if you have to go back after the fact and chart out what his heart rate was. So here's the information. 36 minutes after surgery, that's how many heartbeats he had had in total. 38 minutes, that's how many he had had total. 40 minutes and so forth. See how this works? Total number of heartbeats down here. It's not that his heart was beating at 2,800 beats per minute. Okay? Okay. The monitor estimates this value by calculating the slope of secant line. Use the data to estimate the patient's heart rate after 42 minutes. So here's what they did. Take a good look at this. They computed the heart rate between 36 and 42 minutes. Okay, so we're going to do end beats minus start beats, end time, start time. And let's compute that. Let's do the end time first. What's the end time for A?
42.
42. What's the start time? 36. How many minutes went by? See how this is just like what we were doing? Okay. How many beats had added up after 42 minutes? 29:48. How many beats at 36 minutes? 25:30. Grab your calculators, do the math. We're going to divide by 6. So 29:48 minus 25:40, or we could probably do that in our heads. That's going to be 418. Is that right?
No, 408.
408. No, it should be 418. 418.
Oh, yeah.
Yeah. Good. How many beats per minute?
69.666.
69.6 repeated. Beats per minute. Okay. Now, is that a dumb thing to do? 6 minutes? You're going to average his heart rate over 6 minutes? Okay. Take a look at this. Take a look at C. How many minutes did they average it over here? Only 2 minutes. Is that a better idea? How many minutes did they average it over here? Over 4. Maybe not 6 minutes, 4 minutes, 2 minutes. Do you see what they're doing here? Coming up with an estimate. Somebody tell me about this right here. What did they do there? It's 2 minutes, but on which side of 42 minutes? The other side. Would that make sense? And of these 4 estimates for this person's heart rate, which 2 would be the best? C and D. Okay? And then you could maybe think about, well, gosh, if those are 2 good estimates, how could I make a better estimate given the data that we have? Okay? All right. Any questions? Okay. Let's see. Quizzes here. Grab one before you leave. Okay? And then homework, stack it here. If you've got questions and want to stick around for a few minutes, that'd be great. Thanks.